Your heating system has exactly one job, and the night it fails is the night you discover how thin the margin really is. Picture that moment. The boiler cuts out at 2 a.m., and the cold doesn't arrive like a wave. It seeps. It comes up through the floor, through the gaps around the window frame, through the walls you trusted. The temperature in your home will drop 4 degrees Fahrenheit in the first hour alone. By morning, if nothing has changed, you're looking at conditions that are medically dangerous for anyone over 60 or under 5. The house hasn't collapsed. The roof is intact. But the envelope, the skin supposed to hold warmth inside, has already surrendered everything it had. What most people don't know, what Japanese feudal builders understood at least 400 years before modern construction codes existed, is that the wall itself can be the heat source. Not a conduit for heat, not a barrier against cold. The source. And it doesn't need a single drop of fuel to do it. Walk into a modern home and pull back the drywall and you'll find fiberglass bats, maybe spray foam, maybe a layer of rigid board. Every one of those products is engineered to resist heat transfer, to slow the movement of warmth from inside to outside. That sounds like the right idea. It isn't. Resistance is passive. It slows the loss, but the moment the heat stops being generated, the resistance stops mattering. A well-insulated modern wall holds onto warmth for 2 to 4 hours after the heat source dies. After that, it's just a thin membrane between you and the outside air. The U.S. Department of Energy's own data shows that in a grid-down or fuel-interrupted scenario, conventional well-insulated homes can drop to dangerous internal temperatures within 12 hours in sub-freezing conditions. 12 hours! The modern wall is a holding pen. It was never designed to be a battery. Japanese feudal craftsmen working in the Edo period, roughly 1603 to 1868, built residential and temple walls from a compound called tsuchikabe, meaning earthen wall. These weren't primitive mud daubs. They were engineered multi-layer constructions using specific ratios of clay, subsoil, straw fiber, and sand, applied in sequential coats over a bamboo lattice framework called komai. The walls ran between 25 and 40 centimeters thick. They absorbed heat from indoor fires and sunlight during the day. And then, when the fire died and the temperature outside fell, they gave that heat back. Slowly, steadily, hour by hour, long after the fuel was gone. To understand why that works, you need to understand the difference between two completely different physical properties that the construction industry has spent decades conflating. The first is thermal resistance. Measured in R value, it describes how stubbornly a material blocks heat from passing through it. The second is thermal mass, sometimes called heat capacity. It describes how much heat a material can absorb and store before its own temperature changes. Fiberglass insulation has a high R value and almost no thermal mass. It blocks heat movement but stores almost nothing. Earthen walls have a moderate R value, not as high as fiberglass, but an enormous thermal mass. They absorb heat the way a sponge absorbs water, holding it at the molecular level in the clay minerals and the dense particulate structure of the wall itself. The scientific term for this stored heat behavior is sensible heat storage, meaning heat stored without a phase change, without any chemical reaction, purely as temperature held inside a dense material. The denser and more thermally conductive the material, the more heat it stores, and the more efficiently it releases that heat later. An earthen wall at the correct mix ratio can store up to 840 joules of heat per kilogram per degree Celsius of temperature rise. Fiberglass stores fewer than 20. Think of a cast iron skillet on a gas flame. You turn the burner off and walk away. But the pan keeps cooking. It's not magic, it's mass. The iron absorbed the energy of the flame and holds it at a temperature that keeps working long after the source has gone cold. Now imagine that skillet was your entire wall. Or every square meter of earthen wall facing your living space is absorbing the warmth from your body heat, your cooking, your sunlight through south-facing glass. And it doesn't let go the moment the temperature drops. It lets go slowly, methodically. That is what you're building. The mechanism that makes a 3-day heat cycle possible has a name: thermal lag, also called diurnal phase shift. Diurnal means within a single day-night cycle. And phase shift describes the delay between when heat enters a material and when it exits the other side. A correctly built earthen wall between 30 and 40 centimeters thick has a thermal lag of between 10 and 14 hours. That means heat that enters the wall's inner face in the afternoon doesn't reach the wall's outer face until the middle of the following night. And the same is true in reverse. Cold from outside doesn't penetrate the inner surface until long after you've woken up. The wall is always running on delay, always buffering the extreme, over 3 consecutive days with a modest initial heat input. A single wood fire, a day of passive solar gain through windows, even sustained body heat in an occupied room. The wall's stored thermal energy can maintain an interior temperature above 55 degrees Fahrenheit even when outdoor temperatures drop into the low 20s. The University of Bath Center for Sustainable Energy has documented exactly this behavior in rammed earth and compressed clay wall test panels, noting interior temperature stability of plus or minus 4 degrees over 72-hour monitoring windows without supplemental heat. The wall does not run out, it cycles. Before you mix a single handful of material, you need to understand what you're working with. The primary ingredient is subsoil, not topsoil, not garden soil. But the clay-rich layer that sits below the organic matter, typically 12 to 18 inches below the surface. Subsoil with a clay content between 20 and 35% is ideal. Above 40% and the wall will crack as it dries. You'll test this with a simple jar test. Fill a jar 1/3 with your soil, top with water, shake, and let it settle overnight. The clay layer settles last and sits on top of the sand. Measure the proportions. The second ingredient is sharp sand, not beach sand. Not play sand, but coarse angular sand from a quarry or builder's merchant. The third is straw. Dry, long fiber straw, cut to roughly 4-inch lengths, which acts as tensile reinforcement the way rebar acts in concrete. And you'll need water, clean, and room temperature. Preparation starts with your subsoil. Dig it fresh and break up any clods by hand or with a hoe until you have a consistent crumble with no clumps larger than a grape. For every 3 parts subsoil by volume, you'll add 1 part sharp sand and a generous double handful of chopped straw. That's roughly a 15% straw to mix ratio by volume. Step 1. Combine the dry ingredients in a large trough or on a tarpaulin and work them together until the sand is evenly distributed through the clay. Step 2. Add water gradually, not all at once. You're targeting a consistency that holds a firm ball when squeezed but doesn't leave wet clay smeared on your palm. This is typically achieved at a water-to-mix ratio of around 1:6 by volume. Step 3. Let the mix sit for 20 minutes after initial wetting. This is called slaking. It allows the clay particles to fully hydrate and become workable without being overwet. Do not skip this step. Underslaked mix will crack along stress lines as it dries, and the wall's thermal performance will be compromised at every crack. Step 4. Build your framework. For a freestanding interior thermal mass wall, horizontal wooden or bamboo laths spaced 4 inches apart on a timber frame provide the mechanical key. The rough surface the earth mix grips during application. Apply the first coat at roughly 3 centimeters thick, pressing firmly to work the mix into every gap in the lath structure. This first coat is called the scratch coat, and while it's still slightly wet, drag a comb or toothed trowel across its surface to create horizontal grooves. Those grooves give the next coat mechanical grip. Known Step 5. Allow the scratch coat to dry to leather hard. Firm to the touch but not fully dried, typically 24 to 48 hours depending on ambient humidity. Apply the second coat at another 3 centimeters, working it smooth. Keep the wall surface damp with a light misting of water during the first 3 days of drying. This slows the cure and prevents surface cracking. One natural caution here. If you're building near an existing structural wall, confirm the additional load is within your floor's bearing capacity. Earthen walls are heavy. A 1-meter section at full thickness runs approximately 180 kilograms. Step 6. The finish coat. Mix fine clay with fine sand at a 2-to-1 ratio and apply at 5 millimeters thick. This final layer seals the surface, reduces dust, and provides the smooth, hard face that reflects radiant heat back into the room. The data behind this method is not theoretical. 9 test panels at the University of Bath measuring 300 millimeters thick rammed earth retained interior surface temperatures of 63 degrees Fahrenheit through 72-hour periods with 0 active heating when the test began at an initial wall temperature of 75 degrees Fahrenheit. Research published in the journal Energy and Buildings confirmed that thermal mass walls in temperate and cold climates reduce peak heating loads by up to 30% compared to lightweight insulated frames. And field documentation from a 2019 restoration project of Edo period farmhouses in Nagano Prefecture recorded wall surface temperatures holding within 6 degrees of initial charge after 3 full days, with external temperatures falling to -8 Celsius overnight. 3 days. No fuel, no electricity, no mechanism more complex than physics and patience. The cost comparison is not subtle. High-performance spray foam insulation for a 12 square meter interior wall panel runs between $400 and $600 installed, with a lifespan that degrades after 15 to 20 years as the foam off-gases and loses density. The earthen wall equivalent for the same surface area costs between $18 and $45 in materials. The sand, the straw, the lath framework, if the subsoil is sourced on site, which it usually can be. If you need to purchase subsoil, add no more than $30 to that figure. There is no mechanical component to fail. There is no chemical process to degrade. Properly maintained and kept dry, an earthen wall built today will still be performing at the same thermal specification in 100 years. The foam wall will not. This is not a fringe claim. The German Passive House Institute, one of the most rigorous building performance certification bodies in the world, includes thermal mass calculations in its energy modeling framework and explicitly recognizes high-density earth and clay walls as valid passive heat retention assemblies. Japan's own traditional construction heritage organization has documented Tsuchikabe construction in over 2,000 surviving structures, many of which remain occupied and unmodified. The method has a peer-reviewed record and a 4-century field test. It does not need your faith. It needs your attention. These fuel supply chains are not abstract vulnerabilities. They are scheduled disruptions waiting for the right weather event to become personal catastrophe. Natural gas delivery depends on compressor stations that run on electricity. Heating oil depends on roads that close in the same storms that drop your indoor temperature. The wall asks nothing of any of those systems. You either build the structure that holds heat on its own terms, or you remain dependent on a chain with links you cannot inspect and cannot control. That is the choice. Not someday. Now.